If you could step outside the universe and look down on it, not with human eyes, but with the vision of a god, you wouldn't see isolated stars or lonely galaxies. You'd see threads, vast, glowing filaments stretching for hundreds of millions of light years, interlacing like a neural network made of galaxies, gas, and dark matter. This is the cosmic web, the invisible skeleton that gives the universe its form. Every cluster of stars, every spiral galaxy, every shining quasar is connected through this hidden architecture of gravity. But how do galaxies, these islands of light, emerge from filaments of darkness? How does the cosmic web sculpt the universe we see today? To find out, we have to go back to the moment when structure itself began. After the Big Bang, the universe was almost perfectly smooth. Almost, but not quite. Tiny quantum ripples, differences in density no greater than 1 part in 100,000, drifted through the early plasma. As space expanded and cooled, gravity started to work its magic. Denser regions pulled in more matter, and the faint quantum whispers grew into cosmic harmonies. In just a few 100 million years, those ripples had become sprawling tendrils of matter, the first outlines of the cosmic web. Supercomputer simulations like Illustrious TNG and Millennium Run reveal what this looks like. A universe that resembles a living organism, where each filament acts as a conduit, channeling energy and matter like veins in a colossal being. And it all began with chaos so small, you could fit 1,000 of those first ripples across a single atom. From quantum uncertainty came the map of everything. But visible matter alone can't explain this grand design. The gas and stars we see make up less than 5% of the universe. The rest, the framework itself, is dark matter. It neither emits nor absorbs light, but its gravity sculpts the cosmos. Imagine building a house entirely out of shadows. Dark matter does exactly that, creating the scaffolding upon which galaxies are hung. Wherever dark matter clumps, gravity deepens its wells, pulling in hydrogen and helium gas. These rivers of invisible mass form the filaments, while ordinary matter follows like mist, settling into valleys. Without dark matter, the universe would still be a fog of isolated atoms. No galaxies, no stars, no us. And yet, no one knows what dark matter actually is. Is it made of slow-moving WIMPs, ghostly axions, or something even stranger, like primordial black holes? Each theory redraws the map of the web, changing its thickness, its symmetry, its rhythm. For now, we can only trace the unseen by its pull, the fingerprints of gravity on the light of distant galaxies. As the universe aged beyond 100 million years, gravity intensified the contrast between the dense and the empty. Matter flowed like water through a landscape, draining from vast voids into narrow ridges. These ridges became filaments, cosmic rivers of gas and dark matter stretching across eternity. At the intersections of those rivers, matter pooled into colossal knots, the seeds of galaxy clusters. Astronomers now know that galaxies don't form in isolation. They form along these streams, fed continuously by cold hydrogen sliding down the filaments like rain flowing into lakes. Observatories such as ALMA and MUSE have caught glimpses of these streams in action, ghostly tendrils of gas glowing faintly in ultraviolet light. They call them cold flow accretion channels, and they are the lifeblood of galaxies. Even our own Milky Way still drinks from this cosmic river, pulling in roughly 1 solar mass of gas every year, just enough to keep birthing new stars. The universe, it turns out, doesn't grow old quietly. It feeds, evolves, and renews itself through its own hidden veins. Within those dense knots where filaments intersect, gravity becomes irresistible. Gas clouds collapse, spin, and flatten into disks, the first proto-galaxies. In their hearts, pressure ignites nuclear fusion, and the first stars blaze into existence. Supernovae explode, enriching the surrounding gas with heavier elements. Some cores collapse into black holes, whose gravity shapes the newborn galaxies even further. Each galaxy's destiny depends on where it sits in the web. Those at the intersections grow fast, swallowing material from multiple filaments. They become giants, ellipticals, and cluster cores. Others form along single strands, slowly rotating into elegant spirals. The Milky Way itself was likely born in such a filament, fed by two primary streams of cold gas and small satellite mergers. But the process is violent. Filaments collide, galaxies merge, and gravity tears and rebuilds. The universe's elegance hides a billion years of turbulence. And yet, from that chaos emerges pattern, structure, and the quiet beauty of spiral arms glowing against the dark. Between these filaments lie the voids, immense cosmic deserts spanning hundreds of millions of light years. They are not truly empty, but nearly so. Just a few lonely atoms per cubic meter. Here, gravity is weak and time feels slower. Galaxies that drift into voids become isolated, star formation slows, and chemical evolution nearly stops. These are cosmic fossils, pristine galaxies that have barely changed since the dawn of time. Studying them gives scientists a baseline, a glimpse of what the early universe might have looked like before the Great Web matured. But the voids also serve a greater purpose. As the universe expands, voids grow while filaments tighten. They are the exhalation of the cosmos, balancing the inhaling pull of gravity with the outward push of space itself. If the filaments are veins, the voids are the lungs of the universe, and together they breathe the rhythm of cosmic evolution. For centuries, astronomers thought the universe was random. Only in the last few decades did we glimpse its grand design. Using redshift surveys from Sloan Digital Sky Survey, SDSS, scientists mapped the positions of millions of galaxies, revealing a lace-like structure stretching across the cosmos. But we've only just begun to see its finer threads. The James Webb Space Telescope recently observed protofilaments existing just 400 million years after the Big Bang, a discovery that stunned cosmologists. How could such structure exist so early, when the universe was still a newborn? The upcoming Euclid mission and DESI project will extend these maps in 3 dimensions, tracing both visible and dark matter with unprecedented accuracy. Meanwhile, the Square Kilometer Array, SKA, will listen for the faint whisper of hydrogen across billions of light years, allowing us to literally hear the universe's hidden web. Every observation reveals a new surprise. The web formed faster, stretched farther, and influenced galaxies more deeply than anyone predicted. We are beginning to realize our Milky Way is not an isolated spiral in the void, but one strand in an infinite, shimmering network of creation. The web doesn't merely build galaxies. Galaxies, in turn, reshape the web. When massive stars die, they erupt as supernovae, blasting heavy elements and energy back into intergalactic space. When supermassive black holes feed, they unleash jets that pierce the surrounding gas for hundreds of thousands of light years. This feedback reheats and stirs the filaments, sending shock waves that ripple across the cosmic medium. In this way, galaxies and the web are symbiotic, each feeding, sculpting, and sustaining the other. Some astronomers even call the web a living ecosystem. It grows denser where galaxies thrive, and thins where energy feedback blows material away. Like coral reefs in the ocean, the filaments pulse with life, cycling matter and energy through endless renewal. But this balance won't last forever. A new force is now stretching the web apart. Around 9 billion years after the Big Bang, the universe's expansion began to accelerate. The cause, dark energy, a mysterious pressure woven into space-time itself. As dark energy dominates, filaments begin to thin. Clusters drift farther apart. Eventually, the cosmic web will unravel, its threads stretched beyond visibility. Trillions of years from now, Each galaxy will be marooned in darkness, cut off from every other island of light. The universe will still expand, but its great architecture will fade like mist. We exist at the perfect moment, when the web is visible, its filaments vibrant, its galaxies still talking to one another through light. In the far future, cosmic archaeologists, if any survive, will look into the night sky and see only their own galaxy. They will never know the universe was once so beautifully connected. When you look up at the night sky, you're not just seeing stars, you're seeing the filaments of your own origin. The same hydrogen that streams through cosmic filaments flows through the water in your veins. The same carbon forged in the first filament galaxies forms your cells, your breath, your thoughts. On a biological scale, our neurons form networks strikingly similar to the cosmic web. Both systems balance connection and emptiness, both exchange energy and information, both evolve through feedback and adaptation. Perhaps consciousness itself is another form of cosmic structure, a self-aware filament within a much larger mind. When we map the universe, we are, in a sense, mapping ourselves. 13.8 billion years after it began, the universe stands as a masterpiece of pattern and motion. From quantum ripples to galactic highways, from dark matter scaffolds to spiraling worlds, it all weaves into one astonishing truth. Everything is connected. The cosmic web is not just a structure, it's a story of gravity's patience, of darkness giving birth to light, of simplicity blooming into complexity. Galaxies are not isolated creations. They are the luminous intersections of invisible threads, threads that stretch across space, across time, across you. We are not observers standing apart from the cosmos. We are the cosmos, awakened, curious, and forever reaching along the filaments of understanding.